Okay, so today we are going to start with the probability and statistics. So we've done uh, almost whatever we were required to do in linear algebra. There are a few topics in linear algebra. We are going to revisit them after your quiz. But this is a very small and cute unit. Uh, we will discuss the fundamental laws of probability, some facts about permutation combinations, uh, permutations and combinations. We'll go into probability distributions and characteristic functions. An interpretation of how one makes sense of experimental data, some sort of an application, and maximum likelihood estimate, so on and so forth. So, well, it's an experimental fact that if a coin is tossed 10 times and the ratio n, so coin is tossed n times and nh times heads appears, heads appears, well then what happens to the ratio nh by n as n goes to infinity? Let's say it's a fair coin, a fair coin. Well, we know that from observation this is half, and the larger we make n, the closer this number is to half. So we say that the probability of coming up heads is half. So we say the probability of a fair coin coming up heads is half. Uh, More generally, if I have an experiment performed n times and ns successes I count, then the ratio ns by n, let's say this ratio ns by n appears to approach a limit as n goes to infinity, we say the probability of success is the probability of success is ns over n. So that's the essential definition of probability. The probability, this probability is generally called as a posteriori probability, where we do not attempt to make the prediction of the result. We just measure it. Now, if one attempts to predict probabilities, let's say, then one is led to priori probabilities. Let's say if I have an experiment of n possible outcomes, and through some symmetries or otherwise know that uh, all of these outcomes are equally alike, possible outcomes equally alike. Nothing is special about one outcome that is not special about the other outcome. Well, then, uh, let's say ns of these I define to be success, then the ratio ns by n is the a priori probability of success. So these two type of probabilities, of course, they should always give the same answer. And this is also the schools of thought. This is very close to the frequentist approach, where you define probabilities as a limit of infinite number of trials, for example. And this is, in some sense, a Bayesian approach, close to a Bayesian approach, where you assign some probabilities, you take some events to be equally likely, so on and so forth, and do these things. So, with that introduction, what are the fundamental laws of probability? So, if this all is a repetition for you, it's okay. And this is going to be a very short unit on probability and statistics. But so, let's say we define a few things. PA is the probability of something called A occurring when experiment is performed, when an experiment is performed. So, of course, PA lies between 0 and 1. That's pretty obvious. If A is certain to happen, A is certain, then piece of A is equals to 1. And if A is certainly not happening, then piece of A is 0. Well, to illustrate some more complicated possibilities, consider an experiment of n equally likely outcomes. So, n1 number of outcomes. So we have n, let's say in an experiment, n equally likely outcomes. Consider the scenario. So n1 be the number of outcomes in which A occurs but not B. N2 be the number of outcomes in which B occurs but not A. N3 is the number of outcomes in which both A and B occur, and N4 be the number of outcomes in which neither A nor B occurs. Since we have exhausted all possibilities, n1 plus n2 plus n3 plus n4 is equals to n. This is all that can happen. A can occur, not B, B can occur, not A, both can occur, neither can occur. So now the probability of A and B are obviously given by n1 plus n3 by n, and probability of B is n2 plus n3 by n. We can define some more complicated probability. So what's the probability of either A or B or both occur? So that is going to be n1 plus n2 plus n3 divided by n. The probability of both A and B occurring, both A and B occurring, is called as a joint probability. And that is given by n3 over n. We can define conditional probabilities. Probability of A given that B occurs. So if B has occurred, then the probability of A given B is n3, the favorable outcomes, and B has occurred, that means it's n2 plus n3. Remember, n2 was a probability B occurs but not A, and n3 was A and B has occurred. Okay, what is the probability of B given A? That similarly n3 over n1 plus n3. So this is the probability of B given that A has occurred, and A has occurred is these many number of favorable cases. So what do we conclude? If you look at all the above formulas, we would know that probability of A plus B is essentially probability of A plus probability of B minus probability of AB. So that's the typical Venn diagram we have if we represent the probability of A, B. So probability of this entire shaded region is probability of A, probability of B minus probability of AB. Probability of AB is probability of B into probability of A given B. That's same as probability of A times probability of B given A. So what is the example of this guy? So suppose we have one card drawn from a deck of cards, each of the deck of cards. What is the probability that at least one of them is an ace? So I define the probability of at least one of them being an ace as probability it's an ace on the first deck, and probability that it's an ace on the second that, and we need the probability of either of them or both of them are aces. So that is going to be probability that a card from the first deck is an ace. Remember, there are 4 aces and 52 cards, so it's 1 by 13. This is the probability that B is an ace minus the probability of A and B both, and that's going to be 1 over 169. Remember, because probability of A given B in this case is probability of A, probability of AB is probability of A times probability of B. They are independent decks, so the probabilities are the product. So that's the probability of, you can calculate it, that comes out to be this guy. Uh, okay, so what's the probability of, or what's the example of this formula? So consider other example that what's the probability of drawing two hearts when two cards are drawn successively from the same deck of cards. So probability of two hearts is of course the probability of one heart times probability of one heart given one heart has already been drawn. So that was it. And that's going to be probability of one heart is 1 by 4. Remember, there are 4 colors in each card, and the probability of one heart, given that you've already drawn one heart, that's going to be 12 over 51. And that's going to be 1 over 17. So this is the conditional probability that one heart was already drawn. So there are 12 cards of heart remaining out of the 51. So these were the examples of joint probability and just the union of probabilities. So one more definition is that mutually exclusive. So events are mutually exclusive when probability of both of them occurring is 0, which gives probability of either of them occurring is simply probability of B, this guy. And if probability of AB is equals to probability of A times probability of B, in such a scenario we say that A and B are statistically independent. Statistically independent. Note that this implies probability of A given B is equals to probability of A, and probability of B given A is probability of B. That means the probability of A has no bearing whether or not B has occurred or not. So that is there. Okay, so now what do we have? Well, we can reduce some interesting relations. So for example, probability of A given B is probability of B times probability of A given B. We can also write probability of AB as probability of A times probability of B given A. So from which these two we can say probability of B given A is probability of B, probability of A given B divided by probability of A. This is also known as the Bayes rule, which connects the probability of B given A with the probability of A given B. And more, we can also write this as probability of let's say C given A, that's going to be the probability of C, probability of A given C divided by probability of A. And if we divide these two, we'll get the probability of B given A divided by probability of C given A to be probability of B, probability of A given B divided by probability of C, probability of A given C. So this is the Bayes rule essentially, and one of the simple but a very elegant example of the Bayes rule is, very old problem where you have three drawers A, B, C, and let's say one of the drawers has two gold coins, the other drawer has one gold coin and one silver coin, and the third drawer has two silver coins. Now the question is the following. The question is, suppose one drawer is picked at random and a coin is picked from it at random, and the coin is gold. The coin is gold. What is the probability that the other coin is also gold? So you pick a drawer at random, you take out a coin and it comes out to be the gold. What's the probability that other coin is gold too? Now, if you look at it, we need to calculate. Let's say D denotes the event of D is the event of drawing the first coin to be gold. We wish to calculate probability of A given D. That given that we have drawn the first coin to be the gold, what's the probability that it came from this box? Only then we'll be able to find that the other coin of the box is gold. So how do we do that? Well, we first note that probability of C given D is equals to 0. There's no way a gold coin can occur from this particular drawer. Okay. So now if we calculate the probability of A given D divided by the probability of B given D, the ratio of the probability that it's from the first bag and to the ratio it's from the second bag or drawer, whatever, and we apply our Bayes formula, probability of A, probability of D given A divided by probability of B, probability of D given B, that comes out to be probability of A and probability of B is just 1 by 3. Remember, they were drawn from random, equally likely. The probability of D given A, the probability that I'll draw a gold coin given it was A, was 1, it was a certainty, and the probability of D given that I have picked the second bag was 1 and 2. Remember, the second bag had a gold coin and the silver coin. So the probability of A given D divided by the probability of B given D is 2. I also have one more relation, that is that probability of A given D plus probability of B given D plus probability of C given D is equals to 1. Nothing else can happen. Either it's coming from the first bag, second bag, or the third bag. So combining these two relations, what do I get? I get probability of A given D to be 2 over 3 and the probability of B given D to be 1 over 3, and I already know probability of C given D is 0. So the probability that I'll have the second gold coin is this guy. It's 2/3 of the probability. This is a very simple but a nice example of the Bayes rule. In the next lecture, we'll be doing permutations and combinations. Thank you.